All right, so I'm really, really honored to introduce Karen Emmorey today. She's going to talk. One reason that research on sign languages is important is because it demonstrates something that was just talked about, plasticity. A fundamental dimension on which humans are plastic is that there is more than one language type, one language modality that we can use for the expression, production, comprehension of language. There are at least two, perhaps three language modalities available to us. So in that sense, we are fundamentally plastic with regard to our language capacity. So, as I said, it's my honor to introduce Karen Emmorey. She received her BA, her MA, and her doctorate from UCLA, working with the great and inimitable Vicki Fromkin. So she then braved the traffic on I-5, and I know it was tough. So she braved the traffic on I-5 to drive south to La Jolla to join the great lab that Ursula Bellugi and Ed Klima had established at the Salk Institute for Biological Studies. I, too, was a member of that lab. It's where many of us who work on sign languages got our start. In 2005, she moved all the way across town and a little bit farther south to San Diego State University, where she is now distinguished professor in speech, language, and hearing sciences there at San Diego State University. Now, she can't go much farther south because she's soon going to run into Mr. Trump's wall. So there's not much, she can't go much farther. So Karen has had an extraordinarily productive career. Fortunately, she didn't number all her publications, so I can't report the total number, which would be embarrassing for most of us. So she's worked in a variety of important domains. So it includes imaging research, in which she's looked at this fundamental issue of whether or not the brain recruits the same areas, or whether sign languages recruit the same areas as spoken languages. Are there differences, modality differences, between the brain regions that subserve sign and speech? She has a large body of work looking at various cognitive phenomena, such as working memory or spatial cognition, and looking at what sign languages can tell us about such cognitive phenomena. She has a 2002 book. It's now 2016, but I still find that book very useful as an overview for the earlier work on the psycho and neurolinguistics of sign languages. I recommend it to you as a kind of primer on work on sign languages. Since 2005, she has produced a crucial body of work on bimodal bilinguals. Unlike Spanish-English bilinguals, ASL English bilinguals use two different transmission channels for their two different languages. So this is a fundamentally interesting comparison. What happens with bimodal bilinguals as opposed to bilinguals who use one language modality for their two different languages. So today she's going to tell us about this last body of work, and she's going to tell us specifically about the psycholinguistic, cognitive, and neural implications of bilingual bimodalism. So please give it up for Karen Emmorey.
So how do I get my thing on there? You need to not... Did I do that? There we go. All right. And is my sound good? Sound people are good? Okay. All right. So as you heard, thank you very much, Richard, for that great introduction. So I'm going to be talking about bimodal bilingualism, and as you heard, I'm going to contrast that with what we've been calling unimodal bilingual. So this is where you know two spoken languages. What this means is that you have the same set of linguistic articulators, the vocal tract for both languages. You have the same input channel, auditory perception for your two languages. So unimodal bilinguals. And bimodal bilinguals, on the other hand, have distinct linguistic articulators, so primarily the hands for sign language compared to the vocal tract for spoken language, and you have two distinct input channels, so primarily vision for sign language, audition for spoken language. And for the work that I'm going to tell you about today, we're focused on hearing bimodal bilinguals. So these are primarily people who have been born into a deaf signing family. So they acquire American Sign Language just through exposure from their deaf parents. They acquire the spoken language from exposure to English as the dominant language in the community. So both are acquired naturally. You can think of it as a parallel with someone being born into a Spanish-speaking family with English as the surrounding language of the community. So this is distinct from deaf people who are also bilingual in English and ASL or sign language, but they acquire English in a different way. And so I want to put those guys aside and compare these two groups who are learning language sort of just through the environment, through natural exposure without instruction, for example. And I'm going to talk about three domains where we can learn something by looking at these types of bilinguals. So one is just insights into language selection. So what are the processes involved, the cognitive processes involved in picking which language you're going to use. Then, following on Ellen's beautiful presentation, I'm going to talk a little bit about implications for cognitive control processes and what bilinguals can tell us about that with respect to language selection. And then finally, I'm going to talk a little bit about what bilinguals can tell us about the neural substrates for language. So let me just start talking about language mixing. So what we see is there's a difference in the types of constraints, the articulatory constraints that unimodal bilinguals and bimodal bilinguals are under when they're in a language mixing mode, when they're talking with another bilingual. So what you see with unimodal bilinguals, say a Spanish-English bilingual, is that they switch if they're mixing their language. So they stop speaking English, they switch to Spanish, and then they can switch back to English. Okay? And what's been known actually in this particular behavioral domain is there is a fair amount of evidence that switching does involve some kind of inhibition. To explain asymmetric switch costs, for example, you have to invoke this idea of differential inhibition. So at least within the laboratory, there's a fair amount of evidence that when you go from English to Spanish, you really have to inhibit Spanish, and then you have to uninhibit it to get back to English. Now, bimodal bilinguals can also switch. So I can switch from speaking to signing. But there's also another possibility, which is I can produce a word and a sign at the same time. And we coined this word code blend to get at this idea that I'm not switching between the two, but I'm actually producing a sign and a word at the same time, simultaneous. So this doesn't, of course, involve inhibition because I'm actually producing both languages. But it does involve what we could call dual lexical selection. I still have to retrieve, if I'm going to code blend, I have to retrieve the ASL word as well as the English word. So you could think of that as kind of a dual task. And our first question was just, well, what do bimodal bilinguals do when they're interacting with other bilinguals? Do they switch between speaking and signing? Do they produce code blends? And their preferences might tell us something about the costs or which one is easier. Do they tend to switch? Do they tend to code blend? And that'll tell us about the relative frequency of inhibition versus dual lexical selection. So in this first study, which was done a while ago, what we had bimodal bilinguals do is they would come into the lab, and we were just told them that we were interested in how they talked with other bilinguals. And they had a conversation with a friend. We wanted to really get them into the bilingual mode in Grosjean's terms. And we also had them retell a cartoon to their bilingual partner who they knew. And then we just looked to see how frequently do they switch between speaking and signing, and how frequently do they produce a code blend. And what we found was that code switches were relatively rare. So the blue here is just for the conversation data, and the green is for the narrative. And in both cases, what you see is a much higher frequency of code blending than code switching. And we argued that this suggests that this double lexical retrieval, retrieving two things, was less costly than inhibiting one language to switch to the other. And in fact, we've now done some psycholinguistic studies that I'm not going to present today that show that actually even when you measure the cost of code blend production, you don't see a cost compared to producing each language alone. And in fact, you'll see in comprehension a little bit later in the talk, there's actually facilitation for comprehension for code blends. So it really seems like this being able to produce two elements from your language, from your two languages at the same time, doesn't give a cognitive cost. So let me just give you some examples of what code blending looks like. So I'm going to show you first, this is, because I'm going to show you data from the cartoon. So this is just the very beginning of the cartoon, and then I'm going to show you two clips of code blending that have different characteristics. So first, this is just to show you what the participants are describing, which scene.
Is that Auntie been here from that old putty cat?
Okay, so here's the first clip. So these are both bimodal bilinguals. They're early bilinguals. They come from deaf families. And she's describing this scene. What you'll see is, in this case, English is what we sort of called the matrix language. So the English will sound fine. For those of you who know ASL, you're looking at the signs. The signs are not going to look like great ASL because the signs are kind of following the English. And what you'll see is, I'll just show you some signs that you're going to see. You're going to see binoculars, this. You'll see big eyes, building, across. These are signs, not gestures. Okay? All right.
Oh, and the guy, yeah, binoculars, you can see the cat, you can see the binoculars, you can see his eyes at the end. They're all big. And he's looking out over across the other building, and there's the bird, and you see the bird, and the big eyes of the bird looking at the cat.
Okay, so that was pretty continuous kind of code blending. Sometimes we'll see it where there's just a few signs that are code blended. I'm going to contrast that with this example. I don't know if we can dim the lights a little bit. I apologize, this is early imaging, early filming. We got better later. It looks really good on the screen. So in this case, the matrix language, the one that's providing the syntax, is ASL, is American Sign Language. So when you listen to his English, it's going to sound very odd, sort of like very kind of bad English. And this is because the English is now following the ASL. It almost sounds like you're listening, for those of you who know sign language, English glosses. Okay, and this dichotomy between which language you pick as a matrix language parallels what has been found for spoken language language mixing. So there's a fair number of theories out there that suggest that the syntax has to be provided by one language, and the other language is then the accommodating language. And so we see evidence of that for bimodal bilinguals too. So here's what it looks like when ASL is the matrix language.
First scene, tree, in cage, sing, safe. What? Sea building. Said bird watcher society. And who there? We know. Sylvester. With binoculars. Opposite building. Third floor. Bird. Perfect. Want.
Okay, so you can see that this is quite a rich data set. And actually my colleague Diane Little-Martin is playing around with these data sets now to try to understand the nature of the constraints on when the code blending happens, what are the constraints on the syntactic structure, the semantic structure. What we found in this first study was when you look at the nature of these code blends, they tend to be semantically equivalent, that is translation equivalence. So this fits very nicely with really a very old idea that Pim Leyfeld had, and of course Pim Leyfeld is always right, is that you can really just express one proposition at the same time. So even though you have these two distinct articulators that could allow you to produce distinct propositions, you don't do that. Right? There's a cognitive constraint on proposition expressions. And we find that that's true for our bimodal bilinguals. All right, so let me come back to our basic data, the fact that bimodal bilinguals produce primarily code blends, which doesn't require inhibition of another language. So one of our questions then is, well, is there any evidence that less inhibition or less language control, to be broader, is required for bimodal bilinguals because they don't have to do this kind of switching. They can produce two languages at the same time. So I'm going to present now a little bit of evidence that suggests that there may be less or weaker cognitive control constraints for bimodal bilinguals compared to unimodal bilinguals. So one bit of evidence comes from when bimodal bilinguals are in a monolingual context where their interlocutor doesn't know ASL. Okay? And what we discovered was that these bilinguals, in this case it's an early bilingual, would produce ASL signs to someone who doesn't know ASL. So in this example, this is again telling the Tweety cartoon. And what I want you to do is watch, it's the guy on the right who you saw before is the bimodal bilingual. And if you see his hands, he's going to produce the ASL sign for now. It looks like this, right? As well as a classifier for someone walking back and forth. In fact, someone who's stooped walking back and forth, because this is actually the scene that's being described with Sylvester hunched over. Okay?
So now he's like, scanning, the streets, walking back and forth, trying to figure out.
Okay, I'll show that just one more time.
So now he's like, scanning, the streets, walking back and forth, trying to figure out.
Okay. So we see this with early bilinguals. I'm going to give you one more example. This is from a later study looking at L2 learners. So these are people who learned ASL later in life, basically in adolescence or adulthood. Talking again, someone who doesn't know sign language. This is in a laboratory setting. They're coming in, and they're just asked to describe the scene. In this case, we have it's divided up into segments. And so this is an example where she produces the ASL sign for chase, which looks like this. Right? Okay. Let me show you that.
She went to slam him in the head, and I don't know if she actually did, but she chased him down the street.
Okay. So if you think about this situation, if you're bringing somebody who's a Spanish-English bilingual into the lab, having them retell a story to somebody who is a monolingual English speaker, the chances of getting the number of expressions of a Spanish word to somebody who doesn't know English is really rare. In fact, there's a number of nice studies that demonstrate that unimodal bilinguals rarely produce the wrong word, right? And here we see lots of, in fact, it's even more for the late bilinguals. And we think that's partly because they are acquiring their sign language on top of an English co-speech gesture system that's already there, and you have this interference with co-speech gesture that doesn't occur for unimodal bilinguals. Whereas our native ASL English bilinguals still produce these ASL signs, but a little bit less, and we think that may be because they're acquiring both systems at the same time, English and co-speech gesture and ASL, and they're able to separate those early on. But the point here is this is evidence that you don't have to have as much control over your production compared to unimodal bilinguals because of the existence of co-speech gesture. It's allowed. And people don't even, sometimes people will recognize, oh, that was a sign, because I get caught sometimes. It's like, that's a sign. But often it's not even noticed that something is amiss. And contrast that, whereas if you were to switch to a Spanish word to somebody who doesn't know Spanish. Okay. All right. So one other bit of evidence came from a study that I did with Jenny Pyers, who is herself a native signer, a coda, with deaf parents. And we wanted to look now not at the production of manual signs, but of facial expressions, in particular, facial expressions that mark linguistic structure in sign language. And this study arose in part because of Jenny's personal experience of feeling misunderstood, that her facial expressions were misunderstood by people sometimes. And so we wanted to really investigate that systematically. So there were two types of facial expressions that we looked at. One is raised eyebrows that mark if clauses, conditional clauses. And this is required. So you can have a manual sign like if that initiates a conditional clause, but raised eyebrows across the clause is obligatory, not optional. And those raised eyebrows have to be timed with the conditional clause. So the eyebrows are raised at the beginning of the clause, and they come down at the end of the clause. And that's the linguistic marker of a conditional clause. If you don't have that, then you have a conjoined clause. So in this example, it would mean it snowed and class was canceled, if you follow it up with a statement. The other type of expression we were interested in was WH questions. So these are marked with furrowed brows. Okay? And again, the furrowed brows are obligatory. You have to have them. If you don't have furrowed brows on WH questions, those are considered ungrammatical. So what we did was we had bimodal bilinguals, ASL English bilinguals. These are all, again, CODAs, that is native early bilinguals, as well as a control group of monolingual English speakers. And they were paired with somebody who didn't know ASL, and people knew he was a monolingual English speaker. And they were asked to do two things. One was to describe what they would do in a number of hypothetical situations. So we gave them these hypothetical situations. The idea was to extract if clauses, and also to discover a number of just facts about the interlocutor. So, how many brothers and sisters, where they grew up, all of these WH type questions. So that was to elicit WH questions. And we wanted to look at the monolingual speakers as a control group because people do gesture with their face. They produce gestural facial expressions, and we wanted to sort of see, is there a difference? Do we see raised eyebrows or furrowed brows in the monolingual speakers producing these constructions? Now, this is all in English. There's no ASL involved. This is just interactions in English. Okay? So here's what we looked at. We looked at the percentage of, we'll look at the conditionals first. And we looked at how many of the utterances had raised brows for the bimodal English speakers and how many for the non-signers, the monolingual speakers. And you can see there was significantly more, almost 80% of the English conditional clauses were produced with raised brows. Now, it's interesting that the non-signers, even though they did it significantly less, they also, almost 50% of the time, were raising their eyebrows during these conditional clauses, which is pretty interesting because it suggests maybe there might even be a gestural origin to this linguistic marker that ASL has adopted. But the other possibility is, well, maybe the bimodals are not producing linguistic markers, they're just gesturing more, because there's some evidence that bimodal bilinguals gesture more than monolinguals too. So how do we determine that? Well, one of the things we did was look at the timing, right? Because for the linguistic expression, the timing is critical. The eyebrows have to go up at the initiation of the clause. So when we looked at the timing of these facial expressions, it was only the bilinguals who timed their facial expressions with the onset of the clause. When we looked at the monolinguals, in fact, I think I forgot to put one in here, but they would sort of raise their brows kind of sort of in the middle, not exactly at the beginning. It was very variable in terms of where they produced this brow raise. But for the bimodals, it was consistently produced at the onset of the clause. And so I have one example here. She's really loud, so I want to turn this down. Get this to go down. Okay. So just watch her eyebrows.
Okay, so if somebody shows up like, a colleague of mine shows up like 2 hours late to a meeting.
Okay. All right, so I don't have the monolingual example, but she's not doing that. Okay, so what about WH questions? So this is interesting because what we found was for both groups, they're producing WH furrowed brows significantly less than they did for the conditionals. And in fact, for the monolinguals, the non-signers, we had maybe 5 tokens of furrowed brows when they were producing WH questions. And what we think is going on here is the nature of the social system or the social interaction really disfavors furrowed brows because I'm trying to get information out of you, right? And raised brows is a very open type of facial expression, whereas furrowed brows is very negative. It indicates puzzlement, unhappiness, and so it's not really conducive to getting information if you're furrowing your brows. And yet our bimodal bilinguals still did it, so it means they weren't able to completely stamp out that linguistic effect of furrowed brows being acceptable on WH questions. And this may, in fact, be sort of what gives rise a little bit to the miscommunication or the feeling that the person is thinking, I'm upset, when I'm not upset, I'm just producing a WH facial expression. So let me give you an example. So here's an example. So you want to look, so you can already tell with the still frame, she doesn't look that happy. Okay.
When did you graduate from high school?
Okay. All right. So let me come back to what I was looking at. I think we have now a number of different bits of evidence that suggest that there's weaker demands on language control and inhibition for bimodal bilinguals. One is that code blending is preferred over code switching. The other is that we see both ASL manual signs and facial expressions that are produced when talking with monolinguals. And this is because of the nature of the bimodal aspect of bilingualism. The existence of facial gestures and co-speech manual gestures kind of allows you to have these things leak out. You don't have to inhibit them as much as a unimodal would. So that leads us to this next question, is whether or not we see the bimodal bilingual advantages in executive control that you heard about this morning with Ellen compared to unimodal bilingual. So this is, I'm going to, you've heard this a little bit, but just go through the logic of this idea. So one of the things that no one disagrees about is that both languages are always on in a bilingual, right? And there's lots and lots of evidence that you can't simply switch off one language and switch on the other. You have to control these two. And if both languages are on, then you have competition between the two. And that has to be resolved when speaking in particular, right? And the idea is that the experience in resolving this competition leads to these enhanced executive control abilities. So I've been sort of talking a little bit more about inhibition because of looking at the switching tasks, but I think we can think about it as a general executive control capacity that involves a number of different components, and all of those may be involved in controlling and resolving this competition between the two languages. So what I want you guys to think about with the bimodals is how they can give us a different way of looking at the cognitive processes that are involved or that are critical for resolving this type of competition. So the idea is if some of these advantages stem from simply knowledge and use of two languages, right? Having two syntax systems, having two lexicon, right? Then bimodal and unimodal bilinguals should perform and pattern similarly. Okay? On the other hand, if some of this bilingual advantage comes from the demands of allocating attention to two languages in the same sensory modality, then we may see differences, right? So with production, there's a competition for the tongue. I've got one tongue, only one language can come out. That's not the case for bimodal bilinguals. Also, for perception, if you think about the babies that Ellen was talking about, so unimodal babies are having information coming in either with the same articulator, so visually, or auditorily, and they have to discriminate among languages in the same modality. They have to figure out which language does this input belong to. For bimodal bilingual babies, they have a really clear clue. If it's auditory, you know it's English. If it's visual, you know it's ASL. So they have a really clear cue that helps them do that discrimination task and that attentional task compared to unimodal bilingual. So in both the input and output domains, there's, in a sense, more competition that has to be resolved for unimodal bilinguals compared to bimodal bilinguals. So this is an experiment done with Ellen and Gigi. I didn't know Gigi was going to be here, so this is great. So I will direct all questions to Gigi about this task. But this is, so we did this task with, and I should say this was with older bimodal bilinguals. So I think, of course, older in this case, I think it was like 40-year-old, 50-year-old. So I fall into that category. So this is a flanker task. And so what participants had to do, I don't know if you can see the red flank, the red chevron, you had to just indicate the direction that it was pointing. You had congruent or incongruent flankers, so you have to attend to the direction. You have to monitor and ignore distracting information to successfully do that task. And we also had participants do a go, no-go task. So if the diamonds flanked the chevron, then you would respond to the direction. If the X's were there, then you would withhold response. So you have to monitor the input and then withhold a prepotent response in this case. And then we had the baseline task, which is just indicate left-right, so you can just sort of make sure you don't have any differences in just motor control or the speed of recognizing the chevron or something like that. Okay? So when we had our three groups, we had unimodal bilinguals, bimodal bilinguals, and then our monolingual controls. And here's the data, just looking at mean response times. So for the control, nicely, no difference. If we look at all three of the conditions, both the congruent, incongruent, and the go trials, the unimodal bilinguals were faster than the bimodal bilinguals and then the monolinguals. And if you look at the bimodal bilinguals, they didn't differ from the monolingual speakers. So this is suggesting that at least some of this difference between unimodal bilinguals and monolinguals may be driven by the nature of the input-output systems of their two languages. Now, of course, this is one study. In fact, we have a study with Ellen that is sitting on my desk, in fact, where we do see some evidence that bimodal bilinguals are better than monolinguals when the dual task involves cross-modal integration and cross-modal attention, auditory and vision. But even in that study, there actually are other conditions where the unimodals are still outperforming the bimodals and the monolinguals. So this difference kind of leads us to another question about whether or not bimodal bilinguals, do they really have to engage cognitive control mechanisms at all? I mean, if you have languages in different modalities, do you need to engage these control mechanisms? And what I want to do now is tell you about, are we good? How? Okay. We go to 11:30, right? Okay. Tell you about a study that looked at this to see whether or not we could find evidence that bimodal bilinguals have to use cognitive control mechanisms to control selection of their languages. And to give you some background, we're going to look at a visual world paradigm that's been shown to be sensitive to language co-activation in unimodal bilinguals. So this is work by Viorica Marian with Russian English bilinguals. Hopefully these stimuli are correct. Where your task is simply to, you're told in English, it's all done in English, click on the marker. Well, it turns out that in the display, there's a competitor whose translation in your other language sounds the same. So stamp in Russian is marka. Yeah, good, okay. So what Viorica found was that the Russian English bilinguals tended to briefly look over at that distractor picture, at that competitor picture. The monolinguals didn't. They didn't know Russian. So that was evidence that there's some competition, that when they hear marker, they still activate the Russian word so that they briefly look over at that competitor, and then they resolve that competition. So one question is, well, there's overlap, right? Phonological overlap between the two languages. What about a sign language? Well, it actually turns out that Viorica has done this with bimodal bilinguals. Same paradigm, where now you're asked to click on the cheese. Okay, and the ASL sign for cheese looks like this. Okay. The ASL sign for paper looks like this. Okay. So those are phonologically related in ASL, obviously not in English. There's no overlap. And yet ASL English bilinguals, hearing bilinguals, look at this picture of paper more than monolinguals. So even without phonological overlap, you see evidence of language co-activation. And I refer you to Jill Morford's work for looking at print bilinguals and deaf bilinguals. They show the same kind of co-activation effects through this translation. Oh, I forgot. There's the pictures. Okay. So here's what we wanted to do. First, we wanted to replicate the Marian study, the Shook and Marian study. And we would use looks to that competitor as a measure of language co-activation. So the idea is that the more you would look at that competitor, the more language co-activation that you have. Okay? Then we wanted to measure how good your cognitive control was. So we used a spatial Stroop task that I'll show you. And that gives you basically a measure of your cognitive control. And our question was, are these two measures related? So the amount of language co-activation and how good you are at cognitive control. And the idea is, if we see a relationship between those two, then that's evidence that bimodal bilinguals have to recruit cognitive control mechanisms to manage their language co-activation. So that the better you are at that, the less language co-activation you should see, because good cognitive control, you stamp down that language co-activation. If not, then what it would suggest is maybe to get this kind of cognitive, or to recruit cognitive control, you actually it has to start bottom up. So you have to have some perceptual overlap. So remember, in the Russian case, you hear marker, the competitor is marka. There's perceptual overlap that leads to language co-activation. There's no overlap between cheese, or I should say that's the same thing, cheese and paper, right? There's no fun. So if we don't, it suggests that maybe you have to have this perceptual overlap to recruit cognitive control mechanisms. Okay, does everybody get the argument? Okay, so what did we do? So here's just to give you our ASL visual world paradigm. So it's all in English. These are all hearing bimodal bilinguals with our monolingual matched group. They're matched up like on everything. And so you here, click on the chair. Train is the competitor, so the ASL sign for chair looks like this. Okay, and the ASL sign for train. So phonological overlap. Okay. Of course, nothing in English. So we're going to then measure the looks to the competitor, okay, the train. So here's what we see. This is just fixation proportions, okay? So the target, the thing you're supposed to look at, you see, of course, that in the end, that's where you're looking for both bimodal and monolinguals. What we're most interested in is this difference between the red and the blue. So competitor, that's the ASL distractor sign. You see that the bilinguals are looking more at that compared to the matched distractor one. So this is the one that appears in the same location, has the same frequency, all of that kind of stuff. Monolinguals, no. And I'll zoom in here so you can really see this difference, okay? So this is nice. It replicates the previous studies. What we're going to use then is that proportion of looks to the competitor as our measure of language co-activation across our bimodal bilinguals. And then we're going to compare it with their performance on this spatial Stroop task. So this is the task where you have to indicate with the left-right button press the direction of the arrow. You have a baseline task where you're just, again, like our other baseline task, just doing the direction. Then you have one where it's congruent with the side of the response, so that should be easier, the incongruent side. And what we're going to use as our measure of the Stroop effect of your cognitive control ability is the difference between the congruent and the incongruent trials and the baseline trials. You can also do it with congruent trials, but we're going to look at incongruent versus baseline as a real measure of how good are you at ignoring that irrelevant information. It's a little bit like how good are you at ignoring or tamping down that language co-activation. Okay, so we're going to look at the correlation then between looks to the competitor, amount of language activation, and the Stroop effect. And what we see is there is a correlation for the bimodal bilinguals only, and not for the monolinguals. And this is within the window. Actually, it turns out to be a little bit earlier window than the unimodal bilinguals, and I can sort of talk about why that might be. So it's about 180 to 260 milliseconds after picture onset is where we see this consecutive correlation of 20 millisecond bins for the bimodal bilinguals, but nothing for the monolinguals. And just to convince you that it's really specific to language co-activation, we did a bunch of other analyses. So this is Marcel Giesen is the lead author on this. He's great. So we first looked, okay, what about later in the time period? Because this would be when the language co-activation should have dissipated. Then we don't see any correlation with the Stroop effect. We looked at just maybe overall response time or the baseline response times. Again, no correlation. It's really specific to the Stroop effect, the cognitive control effect, not just general response time. And also we looked at, because one possibility, maybe the bimodal bilinguals just look around more, right? So maybe they look more at the, the control pictures. And no, that's not the case. We found no correlation with looks to the control pictures. So it really seems it's specific to language coactivation. So what this suggests is, first of all, we see that bimodal bilinguals coactivate ASL signs with auditory word recognition. So this is replicating the previous effect. But it also is showing that you don't need to have phonological overlap to have language coactivation. This can happen at the lexical level. It can happen through semantic representations. So it also shows that bimodal bilinguals do have to recruit cognitive control in the same way that unimodal bilinguals have to control their language coactivation. And that this recruitment is not dependent on bottom-up processing, on perceptual overlap. So even when you don't have perceptual overlap, you still have competition between lexical or through semantic representations of your other language that you have to control. Okay, so I think we're doing good. So let me turn then to the last bit of stuff I want to show you, which is now looking at the insights from bimodal bilingualism, or really just looking at ASL, spoken language and sign language, for the neural substrate for language. And what I want to do is show you some data looking at differences between sign and spoken language processing. And we're going to be looking at audiovisual English. So this is watching someone talk, because this is the appropriate comparison if you're going to compare sign language, because sign language is face-to-face. You're seeing the person. So it's not really appropriate to compare sign language processing to reading, for example, which is visual, but it's learned late, and it has a very different kind of system of interaction, or even just disembodied audio speech, because that, again, is not the sort of typical way of interacting with people. So we want to compare audiovisual English with ASL. And then we're going to look at, okay, what's similar by looking at the conjunction. And then we're also, in the same study, look at the nature, the neural response to code blends. So thinking about, people have done work looking at neural responses to code switches. We'll look at what happens with code blends. So here's what the task was. So this was an fMRI study. We had 12 early ASL English bilinguals, and we wanted to engage semantic processing. So this was a task where you had to decide whether the object was edible or not, just to get semantic processing. And we would have, and these, you would either see ASL alone, English alone, or a code blend, and then I'll show you the baseline task. For the code blends, they're always semantic or translation equivalence. So you don't need interpretation here, because the English is going to be the same as the ASL. Okay. You have to decide, is it edible? Okay, here's English. Now you guys who know English can do it.
Bacon. Prison. Salad.
Okay, so here's the code blend condition.
Bacon. Prison. Salad.
And then the baseline is just to control or to subtract from just seeing a person, making a decision. So here you just see the model sitting there silently. There's a dot on the chin, and you just have to press when it turns black, or when it's accompanied with a sound to control for low-level auditory presentation. I think this is just the one without the tone. Very boring. Press the button. Okay. All right, so this is first just looking at the data when you compare it to that control task. Okay, so what you see is, just by looking at the patterns of activation, you can see that there's similarities between particularly frontal temporal regions. But there's also seems to be some brain areas that you see for the ASL condition that you don't see in the English condition. So to really look at this, what we want to do is a direct contrast between the two, each with respect to its control condition, to see which one is significantly different for the two languages. And here's what we see. So blue is regions that were significantly more active for English than for ASL, and orange is regions that were more active for ASL than English. Let's start with the English. So what you see is lots of more activation in superior temporal cortex regions. These regions are auditory processing regions, right? So it's not that surprising, even though there's lots of evidence that suggests that ASL engages these superior temporal regions from other studies, and even in looking at our study, it's way more engaged for auditory processing. So when you're a hearing person processing spoken English, you're really going to engage those continually more than the signers are. And there's even some evidence from Murray and McSweeney's lab suggesting that for hearing signers, these auditory and secondary auditory regions really are tuned to spoken language. And you see activation there for deaf, but not for hearing signers in those regions. Okay, so what about the ASL regions? Well, one region we can look at is these posterior temporal regions. So these are regions that are involved in processing motion and processing sort of visual object recognition. And what we see, this makes sense. I mean, even though you have some movement of the lips for processing spoken language, there's a lot more going on with respect to larger movements of the hands and arms, and you have to do a lot more sort of object recognition, handshake recognition. So the idea is that these regions are more engaged for sign than for speech because of the nature of the articulators and the visual processing of those articulators. Similarly, when we look at ASL versus English, we see more activation in these frontal parietal regions. And our hypothesis for why we see these regions engaged more for sign than for spoken language has to do with the overlap between sort of action observation networks that have been found to be engaged when people recognize just human actions in general. That sign language processing also engages those regions, in particular those regions when they're involved in sort of forward modeling and predicting what's coming up, that you're using these systems of action recognition to help you predict upcoming information. And we see this both for sentence processing as well as for our single sign processing in this case. One other thing to just mention with respect to this difference is the frontal language regions being more active for the ASL than English may be related to differences in ASL and English, but it may also be related to the fact that for our bimodal bilinguals, ASL is their less dominant language. So even though these guys are all codas, they're all very fluent signers, they're still in an English dominant environment. And I would argue that there's almost all ASL English bilinguals, hearing bilinguals are English dominant because of the society that they live in. So it may be that it's that processing, that additional linguistic processing for their non-dominant language that's recruiting those frontal regions. All right. So what about what's the same? So now if we look at the conjunction, what we see is a left lateralized but a bilateral frontal temporal network that's engaged for both ASL and English. And this replicates lots of other studies looking at sort of the common, basically core regions of language processing that are engaged for both signed and spoken languages, despite these big differences in input-output systems. So now let me just turn to the last bit, which is looking at, now we've looked at sort of ASL and English separately. What about code blend perception? Well, let me first show you the behavioral data. This is actually not from the scanner, but from a previous study, just because it's a little bit clearer. So this is looking at the same task. You make a semantic decision, and we're going to compare response times when you do that just with English or just with ASL. And I have two measures here because in the code blend, we're going to measure reaction time for, in comparison with ASL, with video onset. Because you've got transitional information that people are processing early on in the signal. There's no speech yet. So we measure the reaction time for English from speech onset, because you don't have any information before that. What's critical is that for both modalities, we see faster response times for the code blends than for each language alone. So getting that additional semantic information from the other language is speeding your response. Okay, so code blending is actually facilitatory in terms of semantic processing and making these decisions. So what's going on in the brain? So let me just show you the comparison with the control task. And just eyeballing that, you can kind of see that it looks like it's kind of a combination of the two, right? You see the English areas and the ASL areas. So what we want to do is direct contrasts between code blending and signing and code blending in English to find out, do we see, does code blending influence activation within the ASL network or within the English network? Does it change how processing occurs? And do we see any additional areas? So for example, there's lots of evidence, well, I don't know if lots, but there's definitely evidence from the unimodal switching literature that in a switching mode, that you engage frontal attentional regions as well as the anterior cingulate in terms of control. So do we see any evidence that code blending engages those regions to control the perception of the two languages? So let me first start with this comparison between code blends and English by itself. So if you start with the blue, this is regions that have greater activation for code blends versus English. And what you see there is the speech areas, right, the auditory regions, because when you look at code blending, you see the visual areas for sign, right? So those posterior regions that we saw active for sign, you're seeing signs in code blend, but not in English alone. So that's kind of not so interesting. What is interesting is looking at where we see greater activation for code blending compared to English. And where we see that is in this sort of the English region in terms of the left lateralized sort of secondary auditory cortices. What this means is when you're processing a code blend, your brain doesn't have, in that English region doesn't have to work as hard. You see reduced activation. And that parallels the facilitation, the faster response times that we get in code blends compared to English. So code blending is reducing the neural activity in the English network, at least in the sensory region of the English network. Because now I'm going to compare, we're going to do the same thing with ASL. So here, when you look at code blend, more active for code blend, you see the auditory regions, right? So because you're hearing speech in a code blend, but not when you're processing ASL by itself. Again, what's more interesting is this reduced activation for ASL alone, for the code blend compared to ASL alone. So again, these graphs are showing you the percent signal change, and you see for ASL alone, it's higher, both in these language regions, these frontal language regions, as well as in the sensory regions. So again, having the English along with the ASL in the code blend is reducing the amount of work you have to do, in this case, both in language regions, in these frontal regions, as well as in the sensory regions. Okay? And critically, what we didn't see, well, not critically, but we didn't see any additional cognitive control regions for code blends compared to either ASL alone or English alone. So we didn't see additional activation, greater activation for code blends in frontal regions or in these subcortical control regions. So that again fits with kind of what we're seeing is to process these two things at the same time is not engaging cognitive control regions. In fact, it's facilitating processing. It's not costing. Yeah, so this is basically, so getting this and in fact, we have some new data that's suggesting that it really is the semantic content, the redundant semantics, that's inducing this neural efficiency and the facilitation rather than something that's happening at the sort of at the integration at the perceptual level. It seems to be at a higher level. And what we're seeing for ASL in particular, reduced activation in language regions. So English is helping you process the ASL semantically, but also we're suggesting there's some top-down to the sensory level where you get less work in processing the form, either for spoken language for auditory processing or the visual processing for ASL. All right, so let me just sum up the brain stuff. So one of the things that's really interesting about bimodal bilinguals compared to unimodal bilinguals is that you really do have to engage different neural resources for the two languages. So if I was to do a contrast, particularly between very early native Chinese English bilingual, Spanish English bilingual, and just contrast their processing of Spanish with processing of English, I'm not going to get very much leftover activation. I'm not going to see this kind of difference, right? So the question that I think needs more work and more thinking about is what are the ramifications of this? So if you're really using different neural resources, it doesn't seem to be just vision and audition. It seems to then impact other types of systems like feedback systems, prediction systems, other kinds of systems that may be involved that are going to make bimodal bilinguals different than unimodal bilinguals. The other kind of cool thing about looking at these guys is that you can look at the differences, but you can also look at the overlap. You can look to see, okay, where is it invariant? Where do we see modality-independent activation? And that definitely seems to be left lateralized for both. And we do see particularly for face-to-face conversation, we see a bilateral superior temporal activation for both language types. And then looking at code blending, it tells us something about how these two languages then are then integrated when you get them perceived simultaneously. And the integration seems to be both at the language and sensory regions, and we see that in both response time, and we see it in a reduction of neural activation for the code blend condition compared to each language alone. So circling all the way back, what can we learn from bimodal bilinguals? Well, we can look at the nature of language selection processes. What we see for bimodal bilinguals is evidence for less need for control, for cognitive control. They can produce code blends. They prefer to produce code blends. We see production of signs and facial expressions in monolingual situations. This leads to questions about cognitive control. So we may not see the same degree of advantages that we see for unimodal bilinguals. Again, I think it comes back to practice issues. They have a different experience, different type of practice. But they still have to engage cognitive control mechanisms because they have language co-activation. So it may not rise to the extent of seeing a difference between, let's say, monolinguals or unimodal bilinguals and bimodal bilinguals, but they still have to engage those control mechanisms. And by looking at the neural substrate for sign language, spoken language, and actually code blends, we can identify neural invariants. So basically, parasylvian cortex is sort of key language regions for both speech and sign. You can look at the nature of plasticity. So in particular, parietal cortex is clearly playing a different role in sign processing than in spoken language processing. And we can look at language and sensory integration by looking at code blends. So let me end by, this is a big team. I presented lots and lots of studies. Lots and lots of people have worked on these different studies that I've shown. And I want to thank all of the bimodal, bilingual participants and all the monolingual participants. I think it's really important to thank people who volunteer to be in our studies, because without those volunteers, our research is not possible. So all of you bilingual people who sign up for bilingual studies, we really appreciate your help and your work with us. And of course, funding, we can't do this without money. And I'll end with questions. Okay. So I don't know if I think we don't have time for questions. So we'll have to save your questions. You can ask me during lunch or at the discussion.